I'm very passionate about metamaterials and the benefits they bring to the world. I want to show that these benefits can impact every single industry. My personal favorite, as I mentioned, is the medical space, where I think we can have major impact. But every single other one of these applications, we every step of the way show the benefits of metamaterials. So
Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out. And also, we have a free MSE Company Database categorized by industry sector, location, as well as internship and full-time titles. So if you're interested in that, you can find the link in the description below. And now, let's get on to the episode. Hello everyone. Today's guest is George Palikaras, the founding CEO of Metamaterials, Inc., a smart materials and photonics company. Over the past 10 years, he has led Meta to develop disruptive technologies in aerospace, medical, automotive, cleantech, and consumer electronics industries. George completed his PhD in metamaterial science with over 40 journal publications, and he is a named inventor in 30 patents. He has also appeared in Fortune magazine's 40 Under 40 in Greece, as well as Emerging Entrepreneur of the Year by Ernst & Young in Canada. So we're super excited to just hear about your journey while learning about this fascinating world of metamaterials, which I'm still very much confused about. So thank you for joining us today, George.
it's great to be with you. Thank you for inviting me.
Yeah, so just to start off, I think your story of how you got to where you were with spending a great deal of time in school, getting your PhD and having 40 publications, as well as attending business school. When you were in school, did you know you were going to become an entrepreneur? Was this always a goal? Or was this something you stumbled upon as you went throughout your academic career?
So thinking back, kind of all the way back to, I'm originally from Greece. I grew up in a family that was very entrepreneurial. So my dad had his own businesses and run them, sold a few. But generally, I grew up in an environment of risk. And I understood the value of money early on. But just like every Greek parent, they want their son to be a lawyer, a professor, or a doctor. So I kind of followed one of those elements. But even during, as far as I can remember, my years at university, I always had some idea that I wanted to support my group, commercialize or attract business. I remember when I was at Queen Mary University in London, we constantly were pitching for new business, our capabilities, our skills, basically to industry. And that brought me closer to how to pitch, how to basically propose new ideas, and how to win contracts at the end of the day. So there was a skill set that I was constantly developing. But the genesis of me stepping out of that career into an entrepreneurial career was a single point event, which I'm happy to talk about.
Yeah, we'd love for you to get into it and just tell us your story.
So it's a little personal story as well, but that's how you can become passionate about anything you do in life. So during my research after my PhD, I was working on wearable and implantable sensors at Queen Mary University. And at that time, one of my best friends who became a co-founder in the company was a professor at King's College. He's one of the world-renowned professors in imaging, medical imaging to be exact. And during this time when I was doing my research, my wife, who was also working at King's College, she has a life sciences background, got early stage breast cancer. She was very young, around 30. She's a survivor now, 10 years on. And during this time, obviously, there's hospitals, radiation therapy, chemotherapy, etc. And one of the things that was very strange to me was when we were sitting in the hospital room and the radiologist comes over and says, "Okay, George and Nadine, my wife, Nadine will have to measure through a mammogram, which is an X-ray based imaging technology, every single year for the rest of her life. Now, if you know your X-ray technology, it's ionizing radiation, which means that it's harmful. So the more you scan your body, the more chances that you can actually get cancer from scanning your body. So as an engineer, this could not compute. Like, why would you put yourself through that? And I started asking questions about, well, what about MRI technology, magnetic resonance imaging, which is harmless. It doesn't have the same ionizing, it's non-ionizing. And then realizing that there's a lot of false positives with MRIs. Well, what about ultrasound? Well, there's not enough resolution and so on. So we almost like went through every single modality that there was, realizing that X-rays are by far the most efficient in analyzing, even though they create a lot of false negatives, especially for younger women. When the tissue of the breast is dense, they find a lot of cysts. This is normal. It's a natural thing that occurs in female breasts. And one of the challenges is then, what do you do with this? You find a lump. What do you do with it? You have to do a biopsy. So they have to stick a needle, take a little sample, and then test it, whether it's malignant or benign. This is one of the reasons why most women are not tested until later in life. Let's say past their year 45, sometimes 50, and sometimes it's too late. And because you reach at that age, maybe there's something there that you didn't caught early enough. If you have something in the family, maybe the doctors recommend you start a bit early, but again, you run into the risk of ionizing radiation. So suddenly you're testing more to save yourself, but you're in fact harming yourself. And then, of course, the doctors will say, well, it's better to know there's something there than not knowing. And there was one more level of problem with this technology. It is the fact that in order to do a good mammogram, you have to reach the chest cavity, the bone, basically. So the compression that takes place 4 times, so horizontal and vertical times 2 breasts, is extremely painful. So the women that have smaller breasts, they suffer a great deal of pain. And in fact, statistics show that about 1/3 of women, because of the stories, the females share information better than men do when it comes to these medical applications and challenges. They know how painful it is. So some women will avoid doing imaging because of the horrific, painful stories that their friends have suffered over the years. So at that moment, I reached out to my friend, Dr. Panos Kosmas, and he had been developing since his PhD at University of Northern, basically in Boston, Northwestern, I think it's called, or Northeastern University, I forget. And basically at the time, as I said, he was working at King's College. He was developing a radar-based tomographic imaging technology. So this radar-based was different. It was, number one, non-ionizing. It was used on some very old military technology called ground-penetrating radar that was used by the military on aircraft to find mines that were buried on the ground so that you can guide the troops and your vehicles safely across land. So they had taken this military technology, instead of using it to find mines, they were using it to find tumors. And not only using it to find tumors, but to determine whether it was malignant or benign with higher accuracy, even without a biopsy. And it didn't have compression. So everything on paper looked amazing, but there was one fundamental problem. And this is kind of where I come in. So as I said, metamaterials, you actually pointed out, is a fascinating field. This is what I studied. And I, in particular, was working on electromagnetic radiation and control using metamaterials in the early days. So I sit down with Panayotis, and to cut a long story short, we found that the one challenge that was a physics fundamental challenge with this type of imaging, not only radar, but even MRI, anything that's non-invasive and non-ionizing, has a very important property to overcome, which is that the skin either absorbs too much or reflects too much of the energy, and the sensors around it, whether it's an MRI sensor, coil or this radar technique just doesn't have enough signal to pick up and make the algorithms give you an accurate enough image. So this is the eureka moment for me, because I say to him, so are you telling me that if I gave you a material that did what it's called technically impedance matching, and I can make skin transparent to the incoming radio waves that you're sending, that's going to make your life better and it will make your algorithms work better, etc. And so he said, theoretically, yes, it would make a massive difference. So at that moment, I went into the research lab and started doing simulations, as you do. That simulations actually support the theory. And then I was really determined to put together a business plan. And there was a business plan competition at Queen Mary, which I submitted a plan. I pitched my school, won the top prize, which was only £1,000 of money at the time, and said, this is interesting. This could actually not only help people, but it could actually make money, because you have to write a business plan. You have to show that it could be commercially viable as well. So then I took this idea forward, submitted it in a European business plan competition, won that, and that was a little bit more money, like 5,000 euros or something. And it was enough money to put our first patent in place. And the genesis of this company begins at that moment. So putting together a team, co-founders, absolutely not, it's not easy or trivial. There's a lot of work that goes into the founding year, and it's a make it or break it moment. Do you believe enough in this to quit everything you're doing and dedicate yourself? So at the time, I decided to leave academia. I go to industry, get a job, basically, knowing that 1 year later, I'm going to pursue my dream. And even I told my own new boss in industry that I may be, by the way, in a year gone, and they still gave me a job, which was amazing. And I remember every evening and every weekend coming from work at around 5, 6 o'clock and working through almost the whole night and the weekends with my co-founders remotely, simulating these structures, these metamaterial surfaces to perfect these devices and see the benefits, while trying to put together pitch decks and talk to venture capitalists, etc. Ending up putting about $250,000 of my own money to start, quitting my job a year later, like I said, finding some angel investment money, and then we hit our first roadblock, which, to cut a long story short again, led us to aerospace applications. And put the medical side in the kind of the back seat. We realized that starting to speak to medical professionals and venture capitalists, how disruptive this technology was, and realizing it would take us about $25 to $40 million to commercialize this. And we said, okay, typically, this type of medical technologies get incubated at universities, and they are maybe 20 years in the making before a big company comes and licenses the technology, and then they have a lot of resources to commercialize it. So realizing that this dream was far away, and this metamaterial that we invented would make skin transparent and absorb energy to enable a stronger signal through the body. Having about a year into these discussions with a friend led me to find out about the problem with laser strikes in aviation. So we were having coffee with this other friend of mine who was a senior safety analyst for EASA, the European Safety Agency. And the EASA is responsible for, it's like FAA in the States. So they are responsible for the security and safety of all airports, and they make rules and policies, etc. So this is back in 2010, where most people had no idea about this laser strike problem. In Europe, there were people like hooligans in sports events like basketball and soccer/football, where they were lasering the players on the pitch. So they were trying to influence the game with a laser. And then I had no idea that this had already escalated to lasing aircraft. And so I said, okay, so you're saying to me that if I had the material that can apply on the windows, that instead of absorbing energy, which was the medical application, 100% blocks the energy away from the aircraft, this would make a big deal, like a difference in the aviation industry. And that was kind of the genesis of our first aerospace application for exactly the same type of material. It was a metamaterial that instead of absorbing energy, now it would filter it. And we had both Airbus and Boeing competing who would invest in the R&D. Hence, a paying customer meant that we could pivot for a little while into an aerospace industry that basically kicked off this entire business while having some government support and grants to keep the medical business moving forward and gathering all the proof points for the years to come. So I know that it was a little longer than most, but it gives you kind of an idea that you have to really think hard about what your passions are. Every day I wake up, this is really, the medical side is still my dream that I need to complete. This is the reason like I said, became an entrepreneur. And since then, our metamaterials found numerous applications, even within the medical space. We can talk about later on some of these applications.
Yeah, for sure. We'll definitely get into the medical applications. We'll get into the aerospace applications and more. But that was an incredibly powerful story. And it was great to hear some of the advice that you had as well, just in sharing your journey, which ultimately led you to founding this company, Metamaterials Inc. And so we had a segment way back in episode 1 about metamaterials and how they could potentially be used as an invisibility cloak. And that was kind of the extent to what we knew about it. We were like, what is the superpower that this material class has? But we didn't really know the science behind it. So can you explain to our audience and to myself in simple terms what exactly constitutes a metamaterial and maybe how it differs from naturally occurring materials?
Absolutely. So it is a complex subject, as you pointed. So the easiest way to explain what a metamaterial is to give you kind of the theoretical definition and then go into a little bit more practical examples. So a metamaterial is an engineered material, but unlike bulk materials, for example, a lump of gold, where the atoms and the molecules of gold come together in a specific atomic arrangement, so you get the properties of gold. You can control these atoms at the nanoscale on a metamaterial to engineer the properties that you are designing for. So if you want properties beyond the material properties, because you're only bound to, let's say, silicon, and if you look at the periodic table, basically you have your choices. If you want to go beyond these properties that you're naturally occurring in nature, then you start looking into the metamaterial space. Now, metamaterials have one additional benefit, which makes them very attractive from any application that you can think of. They're typically sub-wavelength structures. Sub-wavelength means that they are typically in the order of half, like 2 times up to 100 times smaller than their constituent materials. So if you are doing, I'll give you a very basic example. Think of a lens, the most basic material. You think of a magnifying lens. It's very bulky. It has a specific shape to concentrate light from one side to the other. So imagine that you can take that very bulky lens and collapse it into a flat, ultra thin lens with a metamaterial that can basically control the material properties within that material beyond just pure glass. So what you're given with a glass property, you have to be very precise how to shape that lens to get you your magnification. And once you think about a metamaterial, you can do basically more with less. That makes metamaterials as a category of materials a sustainable approach to material science. If you can do more with less, if you can replace rare earth elements in the periodic table, such as indium, with low cost, more abundant elements like aluminum, for example, or copper, suddenly you have a new field of science that gives you basically less bulk, so less waste, replacing materials that are more exotic with less exotic materials and abundant. That gives you basically thinner, flatter surfaces, which means now for the first time, you can start stacking functions. I mentioned, you can engineer properties. So imagine blocking light and at the same time blocking radiation for low frequency or redirecting a signal for 5Gs, all in the same structure of one engineered material. So the applications are fascinating. The first one you pointed out was cloaking, basically a material that bends light perfectly around an object. And this created a huge amount of interest, as you can imagine, from aerospace and defense initially. That superpower is critical for hiding things. And so in situations like this, obviously, it becomes really an advantage. And one of the things that is important is, the material science for the first time ever, instead of being in the laboratory, like where you're mixing chemicals on a trial and error basis, you can now use what we call material informatics. So to design these metamaterials is kind of the final element, the piece of the puzzle. It's an upside down approach. So instead of being in the laboratory where traditionally you just mix molecules at the molecular level trying to create new properties, if you can engineer the properties with a computer and you have your algorithm and that says, okay, I want this wave function to come out of this material, what is the constituent material that I need to design? So starting with the result and working backwards and basically solving inverse problems, all of a sudden gives you incredible degrees of freedom to design a perfect material for the perfect application. And you do that with a software approach. And the question is not whether it will work, because the math and the physics will tell you, the simulations will tell you if this is feasible. But the question becomes then, can you make it? Can you produce it at a low cost, etc.? And that has been, I would say, the one thing that over the last 10 years, my company has been focusing on, how to create, not just design, but to produce these nanostructures at a relatively large scale and low cost.
Wow, that was literally my next question, is how exactly, I know it's dependent on maybe the specific metamaterial, but how is it formed once you have the simulations and the theory to back it up, and then on the other side, how do you scale that process?
And that's the hardest part, Punith. So when I started the company, I knew how to design metamaterials. My team knew how to design metamaterials. And if you look at the history, there's dozens of research groups around the world. Most of the engineering graduates, whether it's PhD or masters, they typically work for aerospace companies. The aerospace industry understands metamaterials more than any other industry I have come across. Just because of the multifunctionality, they become very attractive to that world where it's seeking the ultimate performance. But there's been a shift over the last few years where we have invented at my company tools that help us leapfrog some of the challenges in making these nanostructures at scale. So when we started the business, for the first 5 years, we were just a design house. We were designing metamaterials, and then we were outsourcing the manufacturing. We were never bound to one type of manufacturing technique. And we had reached out to 2 industries. The first one was the semiconductors industry. Semiconductors are known to have fabrication processes that are extremely precise, but also extremely expensive. So very quickly realizing that this would never scale if we just stuck into the semiconductor industry, where on average a wafer of anything, it's about $20,000 to $30,000. So if you extrapolate that to 1 meter of anything, it's about $100,000. And our first application, as I mentioned, was this aerospace project with Airbus, which had large windows of aircraft. So it was just too expensive for commercial viability at the time. So then the second industry we approached was the industry that made nano and microstructures on film, on foils, companies that are very well known, and like 3M, Fujifilm, Dai Nippon, all these kind of large corporations. And they had a lot of replication tools for microstructures, etc., but not so much for nanostructures. And they were basically not capable of taking us to the right quality, that was the semiconductor design, at the right scale. So we would have to reduce the metamaterial and just make it into a normal coating where you'd lose all the benefits. Our record today is a 40x improvement. So we would get maybe 20% improvements, so 0.2x when working with those companies. So that was a critical point in our life. So this was like around the 5-year mark. We had great applications from our semiconductor partners, not so good on the other side. So there was a cost difference. And that's the key moment in our time where we invent our own tools out of necessity. And we started looking at the world of startups. We acquired another company in the Bay Area, which had the promising technology called rolling mask lithography. And together with our direct write holography, these were the two manufacturing techniques that we invested in to basically take it to the next level, offering semiconductor quality at the speed of like printing newspaper was the goal. And all of that with the target of producing our materials at less than $10 a square meter. And so fast forward to today, we have added with another acquisition last year, nano imprint lithography with roll-to-roll techniques. We have now the capability using that technique to produce 7.5 million meters square of product. The company we acquired is producing nanostructured, beautiful holograms for banknote security, amongst other things. And just to give you an idea, over the strip of this banknote, there is about 4 to 5 billion security features in that one strip on one single banknote. So the industry has been progressing. We have made sure that we stay ahead of the competition. But really now there's going to be a massive acceleration because as these tools are opening up, we are connecting to academia. We are offering up our tools to the next generation of researchers so that they can come up with ideas, just like we did in the first 5 years with design ideas, that we can help incubate and accelerate into the market using our manufacturing tools, which now have a very wide range of capability.
Yeah, that's an amazing story. Again, I feel like Praneeth and I are getting the wisdom of tens of years of experience and struggle. So it's really interesting to see the other side, because normally we just hear about the great applications, but hearing how you get to a point, if you ever want to be an entrepreneur, is very interesting. I think now we want to get into the actual applications and talk about the science. So the first application we want to talk about is in 5G communication, especially in dense urban environments. And in these conditions, there can be dead spots in network coverage due to objects blocking signals. How can this material technology be used to eliminate these dead spots?
Yeah, so we are very proud of our 5G application for a number of reasons. Last year, we won an award from Lux Research on this application. And I'm mainly proud because this is a sustainable application, not just an innovation. It's a sustainable innovation, perhaps is the right word to use. What do I mean by that? When I started my career after the university, I said I worked in industry. So I actually worked in a company that designed and produced base station antennas. And at the time, the hot industry was 3G. So this was a long time ago, but we were working as a contract manufacturer and designer for very large corporations like Sony, Ericsson, Alcatel, Lucent, Nokia, Siemens, and a few others. So we were constantly designing these very powerful devices, and you'd have a range. So on a 3G base station, depending where you put it and how high you put it, you could have, a 5-kilometer radius as what we call a cell. So that's the coverage area. Now, when you take it to 4G, or now more importantly 5G, typically the frequency goes up. So you're going from around 2 gigahertz, or the 3G, area. At 5G, you have different bands. So you have the mid band, which is kind of just a little bit faster than your home Wi-Fi, just over 5 gigahertz. And then you have the real promise of 5G, which is at around 28 gigahertz, which is the millimeter wave band. And at that band, some interesting things happen. First thing is that anything that has water content absorbs the millimeter waves very efficiently. And that means that glass, the trees, human beings, the furniture, they all absorb that millimeter wave band. Unlike 3G and 4G, where the beam bounces from these objects, when the energy gets absorbed, that means that you don't have a hotspot anymore. You have to have more of these 5G base stations spread out, especially in densely populated areas. So you have to basically, almost like it's like fishing with dynamite. Instead of basically being able to attract and spread the 5G network, you have concentrated areas, and then you have dead spots in other areas. So as an engineer, again, there is levels of safety that you can tolerate. And as a human being as well, you want to live in a world that is as sustainable as possible. So I realized with my team that we can create a metamaterial that it is frequency selective. One of the unique things about our material is also it's transparent. Our film is nanostructure that could selectively reflect, redirect, or absorb the 5G signal. And that became the core material. We announced late last year and earlier this year a partnership with Sekisui Chemical, a Japanese conglomerate, to basically take our film into windows, into inside or outside, to basically redirect and enhance the 5G signals without having to have multiple repeaters along, let's say 20 or 30 feet distances. And that means that you have now a totally passive film, does not require any power, and you have to, of course, understand the network, how to set it up. So you need to know where the incoming waves are coming from, and then, like a series of mirrors, redirect the light where you want it. But instead of light, you're redirecting invisible 5G millimeter waves. So that became kind of the concept. We proved out last year with a number of Sekisui's customers that this is in fact very effective. Just a couple of weeks ago after CES, we had Sekisui on national television in Japan, basically showcasing this on national news. And we are very excited because this technology can help really spread the benefits of 5G. But also it does one more thing, which is sometimes people don't realize. I mentioned that it's frequency selective. So as much as we want the signal to come through the building, into the building, we may want to block the signal, redirect it away from an area of choice. Let's say the children's room. So how do you protect, if you're concerned about health, as you should be, how do you protect a room? How do you protect an area? So imagine where our film is probably the only solution in the world that you can get paid for protecting your family, and you can basically put it on your windows where you can rent them out to an operator to reflect away from your house the energy while you're getting paid a small fee for renting out your windows or your office windows, etc. So suddenly this is more than just a connectivity feature. It can be used to also protect, let's say, an area or a space.
Wow. No, that's really fascinating. Is that selective reflectivity, is that same technology? Is that what's important with the MetaAir, the flexible holographic optical filter for the pilot and protection?
It is a very similar, but the difference is that now you're blocking laser light. So this redirect and blocking happens not at millimeter waves, which is the 28 gigahertz, but at very high optical frequencies in the nanometer range. So the visible spectrum, as you know, is from 400 nanometers to 700 nanometers, and basically green is around 532, where you have very powerful lasers. You have the blue lasers, around the 460 nanometers, and then you have the ruby red lasers around the 640 nanometers. So if you can make a film, again, as you pointed out, a filter that perfectly reflects away from an area a specific wavelength, that is what metamaterials can do for you. You can get the benefit of transparency. You still want to fly a plane, right? So you want to be able to cut only specific spectrums. Otherwise, if you cut the whole thing, it's going to look black. So you want to be able to tune only the unnecessary, unwanted attack away from the pilot without affecting his ability to see, and also to see the right colors. One of the biggest innovations in the MetaAir product line was not to block the laser, was actually to make the filter color balanced. What does that mean? A pilot, as they're taking off and landing, the cues that they have, it's just like ours, basically on the street, looking at the traffic light system. You have red, amber, green. The challenge is that in an airport situation, they have a lot more colors, about 6 or 7, and typically they're instruments. So they're trained, as pilots are trained to see all these different color cues as they're performing very stressful, operations, like the takeoff and landing is the most important phases of during flight operations. So imagine putting a filter that filters green. The competition, which comes from a very traditional dye-based technology, very broad band blocking. You take out green, everything looks magenta. So in the eyes at night, it could look red. So suddenly a green light becomes red. That is a visual cue that could be disastrous if you read it the wrong way. So we spend a massive amount of time making our filter perfectly color balanced so that the whites are white and the blues are blue and the reds are red, while at the same time blocking the hazardous laser strike. That was really where metamaterials comes in. Otherwise, you could just use a simple dye-based solution, block the green. It's been done for 30 plus years, but you need something extra. You need something special. And that's when people come to us, when they cannot do fundamentally an application that takes traditional materials, and our redirecting with the 5G example can happen with a normal PCB board. You can do that. You can make a metamaterial out of a PCB board, but it would be too expensive and ugly at the same time. We made it transparent, so you can stick it on a window without affecting the view, and being able to build in all the different functions at the same time. That's what makes it a meta. It goes beyond the normal properties of the materials.
That's really cool. So the last two applications have been with the Airbus or with the MetaAir and the 5G. It's been very much about reflecting or blocking certain wavelengths. Your next one kind of works on this, but I think it works differently. Could you explain about this non-invasive product to monitor blood glucose level by utilizing optical and radio wave sensors and machine learning processing to predict the glucose level changes? So is it roughly the same, or have there been a lot of different improvements made in the space to allow for this type of sensing?
Yeah, anything that is in the medical space, which is going back to the original story of how we came to be. It's about what we call impedance matching. It's making skin transparent and allowing more energy to couple through the skin into the biological tissue so that you can get a good signal and then use the signal to run your diagnostic. You want to measure glucose, you want to find a lump, you want to identify a hemorrhagic event for people with strokes. The list of applications on that is very vast. And we are developing innovations. One of the big projects that we have is non-invasive glucose sensing. Now, this is a very hard topic, hard in terms of science, because the glucose molecule is not super large. It's a small molecule. It is a little smaller than salt in the blood. So our bodies, we eat a lot of salt, and we have basically large concentrations. So glucose would be the next one down after salt. And so one of the first things we did was to define and understand, can we measure and see the difference between salt and glucose? So that was one of our first ever experiments. And we could see the difference between the two molecules. So originally, this technology was kind of thought into the food industry. So can you use this technique to identify when food is going bad, or that you can extend the shelf life of food if it's not going bad? And so that was kind of a qualitative control for the food industry. That was kind of the original idea. And we evolved it to glucose sensing just because we realized how massively important this problem is. It's the holy grail in diagnostics. And one of the things that we were advised to do in the beginning was to test in animals, in particular pigs. And the reason for that was that you could get technologies that were good enough in the normal range of glucose. But what happens at the edges? That's where things are extremely important. So when you're going low in glucose, you can go into a coma. It's a hypoglycemic event. And this is life and death. So you really need to be hospitalized. People with type 1 diabetes will stay, for a day for observation, if not more. So it's a very serious event. In the hyperglycemia, where it's too much, that's where over time comorbidities can emerge. People become blind. They may lose a limb. So this is where your body is running at much higher glucose levels than it should. And then you have obviously your normal range. So we invented these metamaterials to help also enhance the accuracy of glucose sensing. In many ways, we have already proven that this works. We have journals, peer-reviewed journals with our research findings. But to take that base R&D technology that shows that it works and turn it into a fully regulated and tested by FDA product, that goes back to the discussion I had in the beginning, where it's a $25+ million effort. And if it's a class 3, which a continuous non-invasive glucose monitor is under, it's a $75 million effort on average. And the difference is that as a class 3, it's very risky. You have to spend $10,000 per person per trial. A class 2, and that's just to cover insurance if anything goes wrong. And on the class 2B, it's like an order of magnitude less, like $1,000 per person per trial. And you need roughly 10,000 people on a class 3, and you need like 100 people on a class 2. So you can see that the economics start to get way crazy as time goes by. So we have kept a very low profile because of the hype. There's dozens, literally, of companies. Almost every quarter, there is a university that claims that they solved this problem. And we are just taking it very serious, keeping a low profile. We have about 27,000 people registered on our site, waiting for updates, and have offered themselves up to science as guinea pigs. But we have to take step-by-step approach. I hear a lot of companies, Apple, Google, Samsung, many big companies have tried or keep trying, and I have spoken to many of them. The intention is not to make something that's a medical device, but something that's a gadget. So think of as high accuracy as you can get, but you'll read the small print and it will say this is not intended as a medical use, etc., which makes me sad, because they have unlimited resources that if they could put in use, they could if they wanted to, but that's not part of their core business at this stage anyways. I feel that the times are changing because of COVID. I think that the senior managements of companies are pushing the field forward, and they start to care a bit more, and that's a good thing. But again, the underlying technology, we take a multi-sensor approach. We have a millimeter wave sensor we designed, plus a metamaterial and some optical sensors. And that in combination, AI comes to take all this data and really create correlation so that you get accuracy. So our AI approach is to basically create these massive data collection points that are personalized to the individual, and through training of the algorithm, basically become better and better over time. And the more data you have, as you know, in AI, the better your predictions can be. And we believe that through AI, one thing that can happen in this, you have enough data to enter what's called predictive analytics. And in diabetes, this is very important, because if you're going to do an exercise, I know pilots that are diabetic and they have to test before and after each flight because they have to be in full health. I know people that, just normal people that will drive to, let's say, 3-hour journey, and they'll stop 3 times because they're afraid that their glucose will drop below a certain point and fall into a coma as they drive in the highway. So these are very fundamental challenges, of people who want to live their life and they want to have something that's reliable, accurate, and be able to basically give them enough data and a look ahead. This predictive analytics doesn't need to predict the next week. Just to predict the next 2 hours would be fundamentally a step change and a breakthrough in this field.
Absolutely. Yeah. Just from being in the healthcare industry and listening secondhand into some of the challenges these patients face, diabetic patients, it's absolutely wild what they have to deal with. So I'm excited to keep track of this technology and see it come to fruition. But the last application we want to briefly get into before wrapping up the episode is solar films to increase the efficiency of solar cells. And you mentioned on the website your nanoweb technology. So I guess without getting into any proprietary details, we were just wondering maybe generally what structure property relationships allow metamaterials to potentially absorb sunlight from all angles more efficiently than the materials that are used today.
Yeah. So our approach to solar is, again, to be a nanomaterials company. So solar, it's all about light management. How do you manage the light that comes in abundance from up above in the best possible way? So one of the challenges with solar technology is that you hear a lot about efficiency. Oh, this is 30% efficient, this is 40% efficient, this is 20% efficient. But what most people don't realize is that the efficiency happens over a very narrow angular bandwidth. It means that think of it as a cone, if you have your solar cell, you have an acceptance cone that you can maximize efficiency. And if you're outside of this cone, you don't get efficiency. You get nothing. And there's a massive drop in how much of that light coming in at off angles can actually be turned into electricity. So the drop is dramatic. And so if you think of any situation like your home, you have a fixed roof, which means you cannot track the sun. If you have anything that moves, like a car, a train, a plane, like you have the challenge of how can you predict the output of your solar array if you cannot have it within that maximum efficiency output cone all the time. Now, in the solar farm industry, these massive gigawatt installations that exist in the desert and other places, they are energy producing solar farms, but they come with a solar tracker. So you have a hydraulic system that perfectly tracks the sun, sometimes even in 2 axes, because of the rotational movements of the Earth during the year, and basically adjust perfectly throughout the entire day, and then you're within that sweet spot of the cone all the time. Now, it turns out that today, with the price of silicon dropping to record numbers, the actual tracking system has become a little bit more expensive, more than 50% of the overall cost of the solar installation. So think about that for a second. So today, solar technology in a solar farm would be less than 50% of the cost of the overall solar installation. And 50+% now is the tracker. So our thesis coming into this was, can you absorb light at very wide angles? Our target has been 160 degrees without having the need to track. And if you can do that, what kind of materials would you need to use? What would the structure of the solar cell become? And, is this only a technology you can apply to silicon, or can you apply to other types of solar technology cells? There's SIGs, there's 3.5, perovskite, there's a number of types of solar cell types. So we started this incredible collaboration with Enel Green Power. It's a top 10 utility company out of Italy, Lockheed Martin, and got funding from what is the equivalent of the Department of Energy in Canada. It's a $15 million program. We have made a ton of progress despite the delays with COVID and supply chain challenges, etc. This is moving now to areas where we want to demonstrate a 10 kilowatt array in the coming months. And basically, we have a plan put together where this technology will be proven out in the field, in somebody's roof, maybe in Italy or someplace like that. So we have the real data to showcase our technology. But in a laboratory situation, we have already made the nanostructures. We have put them on different types of solar cells. We have shown each component, how it operates. And now we are starting to basically scale that operation to a nearby a near-term plan that helps us commercialize it. It's a very exciting field, and it's a metamaterial that captures light from all angles. It's called a ME resonator. We have partnered with Professor Mark Brogersma, who is a top metamaterial scientist in our field at Stanford University and a couple of other universities, to basically bring these innovations forward.
That's really cool, and definitely would be very big if we can create even more efficient renewable energy. I guess we just want to recap today, but we uncovered the complex world of metamaterials and its endless possibilities, in addition to your entrepreneurial journey in material science. For MSCs who have a passion for technology and entrepreneurship like you, what advice would you give to them based on your experience and what you've learned along the way?
I think that they have to have a passion that they, no matter the ups and downs, will focus their energy and basically will be the reason why they're getting up every day. If they're doing it just for the money, that's not gonna work. They have to have purpose. And just like myself, I'm very passionate about metamaterials and what the benefits they bring to the world. I want to show that these benefits can impact every single industry. My personal favorite, as I mentioned, is the medical space, where I think we can have major impact. But every single other one of these applications, like we, every step of the way, show the benefits of metamaterials. So if you find a problem that's big enough that you are passionate about, it is important that you assess how long it's going to take. You need to have the right support system, whether it's co-founders, investors, university collaborations. Anything that is in the hardware business is hard to do. There was an estimate by my co-founder that it took Tesla 580 man-years until they sold their first, the Tesla Roadster in 2008. That was the level of effort. And, at the time, Tesla had partners, like they had Panasonic for the batteries. They had a huge amount of support. So, in actuality, if you think about the whole project, like the Manhattan Project was 2 million man-years of effort, which is the biggest project so far that mankind has kind of spent time on. But at the end of the day, every single challenge in the hardware business starts with the question, can you make it? So going back 10 years, when I first started, I truly believed that the semiconductor industry would help me make it. They did. But if I knew what I know now about the industry then, I would probably not have started the company. Maybe I would have waited another 5 years, because it was super hard, and demotivating to say, oh my God, I have the product here, it works, but it's ridiculously expensive. Like I cannot really make any profit, any commercial viability out of this. So if you start something, really, especially in the hardware business, you need to know that there are ways to manufacturing that at a cost-effective way. So I would not recommend to follow in my footsteps in that, because we got lucky. We invented techniques that were 6 or 7 orders of magnitude less energy expending, that created a fundamental step change in the economics of the materials that we produced. And finally, if you were going into software, it's not a question if you can make it. The question is, will anybody buy it? And that's really where it's a whole different equation, of how do you look at, creating the next Facebook and the next Google of the world that is driven, by the software. And that's kind of a division in my mind between the two.
Yeah, your passion and knowledge for metamaterials in the space is very evident. So we really appreciate you taking time out of your day to chat with us. We definitely learned a lot. It definitely clears things up now.
It's my pleasure.
Awesome. As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.